Alright guys, where we left off, we found this little ditty to be right up here. 6.25 meters per second squared. When we took the 50 squared divided by the 400, that's how you find centripetal acceleration. That's a little bit of review. But for angular speed at 50 meters per second, okay, so now we're looking at the W thing. So there is a formula for that. I'm just going to do a conversion. It's really all you have to do for this stuff. So angular, I need radians on top. So I'm going to have 6.28. Okay, no, I'm not going to put a 6.28. That's if I'm doing a circle. So what I'm going to divide out by is the distance, which is the radius. What's the radius of this thing? 400 meters? Okay. So I'm going to divide out by 400 meters onto this thing. And that's the distance of one radian or radius. So there you go. So 5/40, that's 1/8 or point, right? Alrighty, so 0.125, what was I thinking? Wasn't that hard at all. 0.125, and that is radian, that's an R, radians per second. Okay, that's the angular speed. Angular acceleration, okay. So it's a constant angular acceleration because the reason we know that, it says uniformly up here. So I'm just going to find the change in speed over here. And I understand that's not in terms of angular speed right now, and that's fine. It's easy to change back. So I'm going to make it easy on myself, and I'm going to go down here to the tangential acceleration, find the change in speed, 40 to 60. So that is 60 minus 40, and that's in meters per second. And that's all divided by the time of 5 seconds to do that. So that, of course, is 20 divided by 5. Now remember, this is 20 meters per second over here, divided by 5 seconds. So that is an answer of 4 meters per second squared. So every second it gets 4 meters per second faster. You might say, hey, why did you do that first? Well, I had those numbers. And now if I want to do angular acceleration, all I'm going to do is convert that 4 meters per second into radians per second without converting both of these numbers, without converting the 40 and the 60 into radians per second. I'm just going to convert one number, which is a lot easier. So now I'm going to convert the 4 for the, go up to do the angular, the 4 meters per second squared. All I'm going to do now is divide out by the meters, and the meters I have is the 400. And so I'm dividing out by the 400 meters. And when the car's gone through through 400 meters around there, it's gone through 1 radian. And there you go, it's 1/100th or 0.01. Now the meters canceled out, so now I'm in radians, that's an R, radians per second squared. Woo, there's that answer. I should start circling my answers. Now it's going to look crazy. Crazy is, crazy does. My mom always used to say. And I did that one earlier in another video. Not doing it again. And the magnitude of the total acceleration. Oh my goodness gracious. Okay, so here's the story. If I can find my thingy. Okay, so we're going around in a track. So the tangential acceleration this way is 4 meters per second squared. As it's speeding up, 4 meters per second squared. But the inward acceleration is 6.25 meters per second squared. I'm not going to do all the math on that, guys. We got better stuff to do tonight than this. Like sleep eventually, I hope. So I'm going to add these two head to tail. They'll tell you the answer to this in a second. So that's the 4. I'm adding this head to tail. That's the 6.25. And they said the magnitude. I guess it's not hard since I don't have to do the angle. It's just you square that, you square that. I guess it's not that hard. I can do a 4 squared plus 6.25 squared. And that equals that. So square root of that answer, 55-ish, is 7.4. 7.4. So I did my Pythagorean theorem and I found this to be 7.4. Once again, that didn't look like a 7. So there's an inward acceleration, the changing motion. And whoops, I got my direction wrong. Well, let's say we're going this way. Oh no, we're speeding up. So we're going this way. I thought we were slowing down. We're speeding up. That was the previous problem. We're speeding up, so we're going this way. So we're accelerating in that direction, but changing motion in this direction. Add the two together. The net change is 7.4 meters per second squared. You don't add an angular acceleration into that because that's not the same as this kind of change in motion. Okay? So you don't add the angular. That's a different kind of acceleration altogether. That's all by its lonesome. Alrighty, so let's check some answers and let's get rid of this pin marking thing. Oops, I said get rid of the pin marking thing. Alrighty, oh, there's no answer, so I guess you'll just have to buy into it. Last thing, guys, there is a direction of this thing. You're going to think I'm crazy on this, but this is what it is. It makes a little more sense when we get an angular momentum. So there is a direction, of course, to angular velocity. It's not clockwise and counterclockwise. It's the right-hand rule thing. I talked about it with torque one time. It's the same idea. Your right hand goes in the direction it spins. Your thumb points in the direction of angular velocity. Done. Okay? That's what you do. Your hand goes in the direction something spins. If it spins the other way, it goes the other way. Your thumb points in. That's the direction of angular velocity. Nope, nothing's moving there. Nothing is moving in the direction of that thumb. Yep, understand that completely. And it doesn't seem to make sense now. But it will make a little bit more sense when we get an angular momentum and gyroscopes and so on. It just doesn't make a lot of sense right now. But that is how you find the direction to your angular velocity. It's the old right-hand rule. And not only for that, but also for your angular acceleration. Whoops. Oh, well, I guess we're still doing this. So that is into the page because your right hand points into the clockwise direction. That means it points into the screen. On the B, your thumb points towards your face because it goes counterclockwise, and that means it comes out of the screen. Okay? A couple examples. Now for angular acceleration, so when you're speeding up, these two are going to be in the same direction, so your thumb's going to point in the same direction. If it's slowing down, the angular acceleration is going to be opposite of the angular velocity. Okay? Just like when you're slowing down in your car. Slowing down your car, the acceleration is in the opposite direction of what you're driving because you're slowing down. Same thing with your angular acceleration. If your wheel is slowing down, your angular acceleration is going backwards to your angular velocity. They'll be in opposite directions. Okay, but that's all, folks. All this stuff is for another time. Okay, that's it. I'm tired. I'm out.